All right, can everyone hear me all right? I can hear myself reverberating, so it's got to be enough amplification there. All right, well, good afternoon, good evening, good morning, wherever you are. My name is Aaron Rossetto from NI, and what I'd like to do in this presentation is to shine a spotlight on some of the RFNoC blocks that we ship within UHD, which is the driver for USRP SDRs, because I'm not sure even people who are familiar with UHD and USRPs realize what's there. There's some really good, powerful blocks that just ship by default that have source code associated with them. And I wanted to make sure that everybody was aware that they were there. So I'll talk a bit about myself. And then for people for whom RFNoC is kind of a foreign concept, I don't have a lot of time in this presentation, but I'll give a very quick overview of what I mean when I say RFNoC. And then we'll look at each of the blocks that I want to highlight. And at the end, I've got a slide on hints and tips for using these blocks. I have been with NI for just about 22 years now, the last 2.5 or so with the SDR squad, and most recently as the UHD maintainer, which is a really great fit for me because I have a long-standing interest in software-defined radio, particularly as it pertains to monitoring public safety communications. So at Barry Duggan's request earlier this year, I gave a presentation to the GNU Radio Amateur Radio Special Interest Group about Project 25 and some of the experiments that I've done with that. And I also presented last year at Virtual GRCon21 that goes much more in depth about RFNoC and some of the changes that we've made to the framework for the UHD 4.0 release. So if RFNoC is foreign to you and you want to take a deeper dive, I suggest taking a look at that presentation. Okay, so the very quick overview of RFNoC is it's essentially a framework for being able to do DSP in the FPGA that you would find on a USRP device that supports RFNoC. And the way that these algorithms are described should be very familiar to this entire audience. They're done in terms of flowgraphs, where in this case, the nodes in the graph are DSP algorithms, and then the edges define the data transfer between them, much as you would draw a flow graph in GNU Radio Companion. So looking at the RFNoC architecture from space, essentially, on the left-hand side, you have the transport adapters, which provide ingress and egress for radio data. In the middle is a big old router that can connect endpoints to each other. And then what I have highlighted in red is what we're going to be talking about today. The computation blocks, the DSP elements that we ship in UHD, or alternatively, that you can create through the out-of-tree RFNoC block creation process, for which we have some really good tutorials that Neil Pandya and Jonathan Pendlum have led in the past, and I think are also available on YouTube. So if you're talking about writing your own DSP out-of-tree block, you'll have to go look at that. But there may be cases where you can get by with some of the simpler, more common algorithms that we have built in to UHD. So for example, I have some code here that creates one of these flow graphs where the radio element is connected to a digital down converter, which in turn is connected to an FIR filter. And then the output of that FIR filter goes to a stream endpoint so that data can be sent back to the host. So like I said, we're going to be focusing on these computation elements, the DSP blocks that are in UHD. And I break them down into 5 separate areas. The first being mathematical operations, second being filtering and windowing functions, the third being ways to get data into and out of a graph that do not end in an antenna, so alternate sources and sinks, stream manipulation, and finally, spectral computation. And on this slide here, the Python logo indicates blocks for which we have support in our UHD Python API. You'll notice that not all of them have it, but that doesn't mean you can't use these blocks from Python. In some cases, like the SplitStream block, for instance, there's really no API to speak of, and you can get a reference to the block because every block has a common base class. And the GNU radio icon beside the blocks indicates blocks for which we have GNU Radio 3.8 support in our Ettus repository on GitHub under the maint-38-UHD 4.0 branch. Yes, we know that's pretty old at this point. We are working to support these on GNU Radio 3.9 and above. So we're getting there. So for each block, what you'll see in the upper right-hand corner of the slide is sort of a graphical diagram indicating the block's input ports and output ports and the data types that they expect. Each block has a unique 32-bit ID called the NoC ID, which is just a little detail, but in a lot of cases, that block ID was chosen sort of cheekily with respect to the actual block. And I wanted to highlight that because there's a couple that actually make me smile every time I think about it. Blocks themselves can be configurable in terms of how the HDL is instantiated in the FPGA so that you can make trade-offs in certain cases between FPGA floor space and capabilities. And those are set in the image file that describes the RFNoC image core that goes on the FPGA as YAML data. And in this example, I've got a DUC and a DDC block where I specifically set the num ports parameter to 1. I think by default, you'll find that the DUCs and DDCs have a pair of ports, but in the case where you don't need that, you want to save some FPGA real estate, you might want to dial that down to 1. And some of these blocks have a considerable number of options to allow you to configure how they are instantiated. And then each block also has some runtime parameters that control its behavior at runtime, which typically your application is going to be involved in setting, whether that is through the GNU Radio Companion block parameters, which is probably the highest level at which you can change these things, or if you have an instance of the specific block controller class via methods on it, either in Python or C++, or going a little bit lower level than that through the property mechanism. A lot of these blocks advertise properties and there's a generic set get API, which can be used if the block doesn't have a block controller because these are part of the block controller's base class. And then at the very lowest level, you could actually do direct register writes to the block's register map if you wanted. I would advise you not to do that because there's danger that way. It's extremely tricky to get right, and you're better off using some of the higher level ways to access these parameters because the higher level you get, the more support and help and less probability of you really messing stuff up. Okay, now onto the blocks, beginning with the mathematical computation. The first one is the adder-subtractor block, which has an RFNoC ID of hex, ADD, and a bunch of zeros. Get it? Because it adds. This block, pretty simply, takes two input streams of signed 16-bit complex data and then produces the sum and difference of each sample at its output. Very, very simple block, but it illustrates how to use either Verilog, VHDL, or HLS in the block design synthesis. And we provide, I think, implementations of all three of those in UHD, and then that useImpl parameter will tell the framework which one to instantiate and use when you use the block. I think by default it's Verilog because most of the blocks are in Verilog, but if you wanted to see how you could write your own block in one of these other HLSs, this is how you would do it. Okay, the next block is a log power block that computes an estimate of that formula, which didn't render correctly. Awesome. That's supposed to be log to the base 2 of the square root of I squared plus Q squared, but you probably already knew that. And then stores the result, which is a scalar value, in the upper 16 bits of each 32-bit output item. And there are parameters here to add some random noise to kind of spread out the quantization error. Moving average block does exactly as it sounds. It takes in a stream of samples, it sums the last n samples and divides it by a divisor and outputs that through the output port. And in this case, you can control the length and the divisor at runtime. Okay, onto the filtering blocks. We have the classic FIR block that everybody knows and loves, but it is extraordinarily configurable. and I list the parameters there. This allows you to make some trade-offs between the way that the FIR filter should work based on your application and how much FPGA resources it will need to be able to be instantiated. For instance, if you don't need to reload coefficients at runtime, if you just have a fixed set, then you can disable reloadable coefficients, save yourself some registers. Similarly, if you have symmetric coefficients, then you could save multipliers by enabling that. Or skip zero coefficients assumes that in your runtime parameters, any zero coefficients will remain zero coefficients. They'll never change, which is useful for things like half-band filters. And the coefficients can be changed at runtime, again, assuming that you've enabled the reloadable coefficients parameter, which I believe is true by default. All right, we also have an IIR filter that implements a variable length delay line with runtime configurable alpha, beta, and delay parameters. Pretty straightforward and a pretty poorly rendered function. Cool. And then there's your standard window function typically used before an FFT. Does exactly what it says. For each input sample, it multiplies it by the window coefficients and then outputs the result to the output. You can set the maximum window size in samples, which you'd want to make a power of 2, and that would give you some control over the number of registers that are used to store the coefficients. Okay, on to the sources and sinks. First one is the null source sink. This is a very, very simple block that, as a source, produces incrementing sample data that you can also have throttled, so that you won't constantly spam the bus with data. You can have it wait a certain number of clock cycles before producing the next sample output. It can also slurp in whatever data you put into the sink input, and then anything coming into the loopback input goes directly to the loopback output, and there are counters on each of these. So you can monitor the counters to make sure that you are seeing the expected number of samples that you want. Now, given the source data being incrementing samples, isn't particularly useful. It's probably not going to work well with your DSP, but it's great for just testing flow and getting things working in the first place before you start using your actual source, like a radio, for instance. I want to spend a little bit of time talking about this block because it is a very useful block. So what it does is it replays sample data that is stored in RAM, or stores incoming sample data into that RAM, and you can kind of play back and record at will. So I liken it to a Cheddar VCR. The one thing I will say about this block is that in a lot of cases, the block controller API and the set of properties that a block advertises are pretty similar. In a lot of cases, they don't diverge greatly. This is one case where they kind of do, because Michael West and my colleague Matt Prost put a lot of time and effort into designing a really good API to make using the replay block as simple as possible, because there are some caveats here. Samples need to be aligned correctly based on the size of your RAM data bus, for instance, and things have to be at sample boundaries. And that API will enforce that and will make sure that things are coerced such that you'll have the best chance of success. We also ship an example that uses the replay block, and now I believe it is part of the default image on the X330 and the X310, and I want to say the N310 as well. So the latest images will have these on there for your use, connected directly to stream endpoints. Again, to lower the activation energy of getting one of these things to work in your design. Okay, the KeepInN Block, pretty simple. We'll forward the first of a sample or of a packet and then discard the next n-1 samples or packets. And whether it discards samples or packets is controllable via a parameter, naturally, where the packet size is denoted by the assertion of the TLAS signal in the AXI stream protocol. And at runtime, you can set that end parameter as well as the mode. The SplitStream block seems conceptually very simple, and it is. Given a number of input ports, it will split out that signal to some number of branches so that you'll end up with number of inputs times number of branches, output ports, just repeating that data. And while it sounds very simple, there is a little wrinkle here, and it has to do with the RFNoC architecture and features that we call property propagation and action propagation. So the way that this block forwards any actions or properties that comes in on these edges is a little bit tricky. And I wrote the block controller for this block. So I made sure to put a really good comment in the header file indicating the rules for, well, when an action arrives on an output branch of an output port, it will be broadcast here. Or when there's a property propagation event, it will forward this way to these ports and these branches. So it's worth taking a look if you should decide that you want to use the SplitStream block in your application. And then the switchboard block was contributed by a summer intern that we had last year, Jesse Zhang. And what it does is switches any input port, allows you to route it to any output port. The block controller has a really nice API. It's a single function called connect. You give it the input number and the output number, and it will make that connection. If you decide to use the properties to talk to this thing, you have to set the input select and the output select separately. So again, here's another case where there's a nice API, but you can still use the properties, and it takes a little bit more effort to get them to work. All right, now on to the last chunk of blocks, sort of the spectral blocks. There's the digital down converter and up converter, which are part of, I think, every default RFNoC image following the radio, right? Which is where you'd expect to most often to have it. Lets you set the input rate and the output rate, or if you're using the property mechanism, I think we break out the ratio property separately. So if you wanted to work in terms of ratio, then you could set the property. Otherwise, you can do. Otherwise, you could set the input rate and the output rate, and it will do the math and set the ratio for you automatically. All right. So the FFT, everybody knows and loves the FFT. And as I was putting together this presentation, I thought it was kind of strange the selection of options that it provided. There's a way to tell the block that you want either complex output data, magnitude data, or mag squared data. And then the shift parameter indicates how that data should be arranged in the output stream, whether you want the DC component first, followed by positive and then negative frequencies, or if you want the negative frequencies and then your zero component in the middle, then positive frequencies, or completely backwards, the other way around. And it was interesting to me, why might this block support these things? And I was listening to, I have to admit, I've been fascinated by Hash's talk on Monday about looking at power meter data. And he was talking about Sandia Labs' frequency hopping spread spectrum toolkit and how he uses that to get to look at the entire ISM band and to have tagged messages from power meters, which worked better, he was saying, than having a really big polyphase channelizer, which, you know, took up all the cores of his CPU and probably GPU as well. And I thought, well, that's fascinating. I would love to see an RFNoC block that did what some of these Sandia Labs tools do. So I was looking at the code to see how feasible this was. And the first thing that the code does in its work function is it takes a coarse FFT of the incoming spectrum, looking for areas with higher power, then it focuses in and does like a frequency correction on them. Well, if you look at the code, it does an FFT, then goes across those samples, computing mag squared, and then rearranges them to have the negative frequency components first, followed by the positive frequency components, because I guess they're not like that in whatever implementation of the FFT he was using. And I'm looking at this and thinking, oh, wow, we have an RFNoC block that does that already. So I guess the point here is I'm really excited about reading my power meter, and that there's a reason for some of these configurations that we offer, and that it's there. So I can sort of really quickly get started on prototyping something just with this in-tree block. And then finally, the world famous Phosphor Block. You can see it in the demo that we have in the Expo Hall. What the Phosphor Block does is it accepts FFT input data. So you need to do an FFT before it, and produces two output streams of 8-bit data. One is histogram data, which is the upper part of that display, and it's sort of a heat map of each of the frequency bins of the FFT on the x-axis. The y-axis has different power bins, and as the Phosphor Block reads FFTs, it accumulates the values in each of the frequency bins based on power, and then the brighter colors, based on the color scheme that you choose, indicate where the vast majority of each frequency bin, where the power was spent, right? And then that red line that you see is a peak hold that can decay at a configurable rate. We also show the average in there. You can't see it. It's a thin white line. And at the bottom is waterfall data, which is a historical view of the power in each of the FFT frequency bins that scrolls over time. So it's a pretty specialized block, but it's great to make really dynamic, visually appealing demos, and very quickly allows you to visualize a spectrum. And there are a ton of runtime parameters here. And as we and my colleague Wade Fife were trying to figure this out, we made sure that we documented what we figured out as we sort of reverse engineered how this stuff worked, because there was no comments for it before, and we added those comments into UHD. So hopefully if you decide to use the Phosphor Block, those comments will help guide you into setting these parameters appropriately. So finally, for my hits and tips, I've said a number of times, go look at the source. I like to think we do a pretty good job of documenting things, but also a lot of these blocks have a very good comprehensive test bench that you can look to understand exactly how it's going to work in some of these more rare configurations. And like I said, the block controller header files usually have really good comments about how each of the functions works, what it changes, and the range of values that it allows, as well as the RFNoC Block Verilog file as well has a lot of additional details. And like the replay block, some of these blocks have C++ examples that are in the host example subdirectory that you can take a look at to see how you can get these to work and how to correctly configure them. And speaking of configurability, as you saw, some of these blocks have a lot of different configuration that in some cases may not make sense when set a certain way. So if you are using sort of a non-default configuration, just take care and make sure that you're not getting any unexpected data or unexpected behavior, because that can happen when you set an invalid sort of combination of some of these things, maybe in some of the use cases that were more lightly tested than some of the other more common ones. All right, and I'm going to be here until Friday, so please come and see me if you have any questions. Come to the Expo Hall and see the Phosphor Block in all of its glory. And I'll be on chat too, monitor that, see if there's any questions there. But with that, I think that's my time. Thank you very much for your attention.
Thank you, Aaron.